Hello and welcome to this session. In this session, we will discuss about simplex methods to solve linear programming problems. We are already familiar with the method of solving a linear programming problem graphically. We can solve a linear programming problem graphically when we have only two unknown variables. If we have more than two unknown variables, maybe 3, 4 and so on, then we cannot solve the linear programming problem graphically. To solve a linear programming problem which involves n number of unknown variables, we use an algebraic method called simplex method. Here we will discuss this method for standard maximization problem. A standard maximization problem in n variables x1, x2 to xn is one in which we have to maximize, not minimize, an objective function of the form z equal to c1 x1 plus c2 x2 plus so on plus cn xn, subject to the constraints a11 x1 plus a12 x2 plus so on plus a1n xn less than equal to b1, a21 x1 plus a22 x2 plus so on plus a2n xn is less than equal to b2, so on am1 x1 plus am2 x2 plus so on plus amn xn is less than equal to bn, where all the bi's, where I equal to 1, 2 and so on till m, are non-negative. The inequalities used in these constraints are less than equal to type. They cannot be equal to or greater than equal to. Also, all the variables xj's are greater than equal to 0 for j equal to 1, 2, 3 and so on till n. For example, our problem is maximize z equal to 2x1 plus 3x2 plus 4x3 subject to the constraints 3x1 plus 4x2 minus x3 less than equal to 5. Second constraint is x1 minus 2x2 plus x3 is less than equal to 4, where x1 is greater than equal to 0, x2 is greater than equal to 0 and x3 is greater than equal to 0. This is a standard maximization problem. Now we will discuss the steps involved in solving standard maximization problem using simplex method with the help of an example. Consider the following linear programming problem in standard maximization form. Maximize z equal to x1 plus x2 subject to 2x1 plus x2 is less than equal to 4, x1 plus 2x2 is less than equal to 3, x1 is greater than equal to 0 and x2 is greater than equal to 0. It is a standard maximization problem and we will solve it algebraically using simplex method. Our first step is to write the given linear programming problem with constraints having equal to symbol. It means the constraints in less than equal to form should be written in equal to form. For this, we will make use of slack variables. We will add x3 and x4 variables such that x3 is greater than equal to 0 and x4 is greater than equal to 0 to the given constraints so that we can write it in the equal to form. So we get the following constraints: 2x1 plus x2 plus x3 is equal to 4, x1 plus 2x2 plus x4 is equal to 3, x1 is greater than equal to 0, x2 is greater than equal to 0, x3 is greater than equal to 0 and x4 is greater than equal to 0. Note that while writing these constraints, always write the same variable one below the other. Also, we can write the objective function z equal to x1 plus x2 as z minus x1 minus x2 equal to 0. So now we have the following equations: 2x1 plus x2 plus x3 is equal to 4, x1 plus 2x2 plus x4 equal to 3, minus x1 minus x2 plus z equal to 0. Note that we have written the objective function in the last. Now our next step is to write the initial simplex table. In this step, we will form a table. In these three equations, we have z, x1, x2, x3 and x4 variables and their respective coefficients on the LHS. That is the left hand side. And on the RHS, that is the right hand side, we have 4, 3 and 0. So now we have written all these terms in the form of a table. First we have filled up the columns of x1, x2, x3, x4 and z. In these columns we have written all the coefficients of the variables from the equations. These columns form a coefficient matrix of the given equations. And in the last column we have written the values written on the right hand side of the equation. Now see, the columns of x3, x4 and z are forming an identity matrix 1 0 0 0 1 0 0 0 1. So the variables corresponding to these columns, that are x3, x4 and z, are called basic variables, and we write them in column 1. Note that always write z in the last row for the convenience of calculation. Our next step is to determine the entering basic variable. To select the entering basic variable, we look at all the numbers in the bottom row, that is where we have written z, in last row excluding the last entry on the right hand side column. So here we have drawn darker lines in the table to show what is being excluded. This is the first iteration. Now we have -1, -1, 0, 0, 1 in the last row. From these, choose the negative number with the largest magnitude or the most negative number. That column is called as the pivot column. If there are two or more numbers having the same magnitude, choose any one. If there are no negative numbers to choose, that is, if all values in this last row are positive, then we get our optimum solution. And the current basic solution will be the optimal solution. Here we have two negative values, -1 and -1. Both have the same magnitude, that is 1. So we can choose any one of x1 and x2 as the incoming variable. Let us choose x2. So we choose x2 as the entering variable. We put an arrow here. So x2 column is our pivot column. It means that x2 will enter the basis and one of x3 and x4 will leave the basis. Now our next step is to select the pivot element and the outgoing basic variable. To select the pivot element, we follow the following rules to decide which of the entries in the pivot column will be the pivot element. Negative values in the pivot column will not be considered. For each positive entry V in the pivot column, compute the ratio U by V, where U is the number in the rightmost column, that is the RHS column. We call this test ratio. That is, we find ratio by dividing element of the right hand side column by the corresponding positive element in the pivot column. Of these ratios, choose the minimum ratio. The corresponding number V is the pivot element. The basic variable corresponding to the smallest ratio will be outgoing variable from the bases. Now see here, x2 is the pivot column. It has both elements positive, 1 and 2. In the first row, v is 1 and u is 4 in RHS column. So we calculate the ratio u by v, that is 4 upon 1, which is equal to 4. In the second row, v is 2 and corresponding u is 3. So u by v, that is 3 by 2, is equal to 1.5. Now 1.5 is minimum of the two ratios and it is corresponding to v equal to 2. So we choose 2 as the pivot element in the pivot column. Also, the corresponding basic variable to this pivot element is x4. So x4 is the outgoing basic variable we mark an arrow here. This row is called the pivot row. Our next step will be to solve for new basic feasible solution by using elementary row operations to construct new simplex table and check for optimality. To find new basic feasible solution, the pivot element must be made equal to 1 and all other elements in the pivot column should be equal to 0. Now x2 is the new basic variable. We have to make the pivot element in the entering basic variable x2 equal to 1 and all other elements in the pivot column equal to 0. So we will convert entries 1, 2, minus 1 to 0, 1, 0 in x2 column. To change elements in the pivot column, we will apply specific row operations. So all the values in the table will change according to the operation used on each row. The specific elementary operations are divide, pivot row by the pivot element. For each other row, including the last row, corresponding to Z, that has a positive entry in the pivot column, say S. Use use operation Ri goes to Ri minus SRP. That is, ith row goes to ith row minus S times the pth row, where Rp is the pth row, the new pivot row obtained by dividing with the pivot element. For each other row, that has a negative entry in the pivot column, say T, take absolute value of T and use operation jth row goes to jth row plus absolute value of T times pth row, where Rp is the pth row, which is the new pivot row obtained by dividing with the pivot element. Now let us come to the example. To change the entries in the pivot column, we now use the above mentioned procedure. So now we convert the pivot element 2 to 1. Here we have the pivot element 2, so we will divide the whole pivot row by 2. So we have the following table. The first row is as it is. In the second row, we use the operation R2 goes to 1 by 2 R2. So we have half, then 2 by 2, that is 1, 0 by 2 is 0, half, then 0 by 2 is 0, and in the RHS we have 3 by 2. The last row also remains as it is. Now we have to make all other elements in the pivot column 0. So for this we will apply row operations on row 1 and row 3. Now, as discussed, we know for each other row, including the last row corresponding to Z, that has a positive entry in the pivot column, say S, use operation ith row goes to ith row minus S times the pth row, where Rp is the pth row, is the new pivot row obtained by dividing with the pivot element. Here Rp is R2 obtained by dividing pivot row by 2. So in row 1 we have positive values 1 in the pivot column. So we choose operation Ri goes to Ri minus SRP, which is equal to R1 goes to R1 minus R2. Now on row 3, we have negative value T equal to minus 1 in the pivot column, its absolute value is equal to 1. So we choose the operation Ri goes to Ri plus absolute value of t times Rp equal to R3 goes to R3 plus R2. In the first row, we have 2 minus 1 by 2 equal to 3 by 2. 1 minus 1 is equal to 0. 1 minus 0 is equal to 1. 0 minus 1 by 2 is equal to minus 1 by 2. 0 minus 0 is equal to 0. And 4 minus 3 by 2 is equal to 5 by 2. In the third row, we have minus 1 plus half equal to minus 1 by 2. Minus 1 plus 1 equal to 0. 0 plus 0 equal to 0. 0 plus half is equal to 1 by 2. 1 plus 0 is equal to 1. And 0 plus 3 by 2 is equal to 3 by 2. And the pivot row, that is the second row, remains as it is, that is 1 by 2, 1, 0, 1 by 2, 0, 3 by 2. This is our second iteration. Here we have minus 1 by 2 in the last row, so it is not an optimal solution. So we continue to the next step. Now we have to repeat steps 3 to 5 until there are no more negative numbers in the bottom row, with the possible exception of the RHS column. That is, we take the most negative number in the bottom row of the current table, excluding the rightmost entry, and repeat step 4 and step 5 to obtain the next iteration, and so on, until there are no more negative numbers in the bottom row, excluding the rightmost entry. Now here we have minus 1 by 2 as the negative number in the bottom row. So we choose x1 as the entering variable, and it is the pivot column. Now we choose outgoing variable using the same method used in step 4. We find ratio by dividing element of the RHS column by the corresponding element in the pivot column. We get 5 by 2 divided by 3 by 2, which is equal to 5 by 3, which is equal to 1.6, and 3 by 2 divided by 1 by 2, which is equal to 3 divided by 1 equal to 3. So 1.6 is minimum of both the values. So x3 is the outgoing basic variable and 3 by 2 is the pivot element. So we write x1 in the entering basic variable in place of x3 in column 1. Now we have to make 3 by 2 as entry 1, 1 by 2 as entry 0 and minus 1 by 2 as 0 in the pivot column. So first we make the pivot element 1 by using the row operation R1 goes to 2 by 3 R1. So in the first row we have 1, 0, 2 by 3 minus 1 by 3, 0 and 5 by 3. All the other entries remain the same. Now to make all other entries in x1 column 0, we use the following operations on row 2 and row 3, that are R2 goes to R2 minus 1 by 2 R1 and R3 goes to R3 plus 1 by 2 R1. Now all the values in the bottom row corresponding to Z are positive, so we are done. RHS column gives the solution to the linear programming problem. Corresponding to x1, we have the value 5 by 3 and corresponding to x2, we have the value 2 by 3. So, the solution to the linear programming problem is x1 is equal to 5 by 3 and x2 is equal to 2 by 3. So, maximum value of Z is equal to x1 plus x2, which is equal to 5 by 3 plus 2 by 3, which is equal to 7 by 3. This is the required method of solving a standard maximization problem. This completes our session. Hope you enjoyed this session.